Welcome, everybody, to Matter and Meaning, where we try to find meaning from the matter around us. Right now, I am the host, Jack, and I have.
I'm Ben. We've met before. The first podcast has just come out. We're recording this one quite far in advance, I think, now, isn't it? I'm not sure what audio you're trying to bring them out.
Yeah, we're recording quite a few of them in advance, so this might be a while before anybody sees it.
Yeah.
And we have a special guest today.
So I am Chris Allton. I'm a professor lecturer in physics in Swansea University.
All right, so I guess we can kind of just get right into. Oh, actually, first before we get into it, I just wanted to take a second to thank you and also to thank everybody that we've already interviewed, because the only way that we can do this podcast is if people are kind, and the people who we interview usually don't get anything from it. We're the ones getting all the reward. So I really appreciate it. And I guess we can get into it then.
Yeah.
So just to start us off, what did you do your PhD on?
So I did my PhD many years ago. It's sort of in particle physics, but I would say more what you call statistical mechanics, which is studying the physics of very large numbers of bodies, particles.
Mm-hmm.
So the obvious application of that is studying gases. So if you sort of study the motion of, let's take a cricket ball, the motion of that through the air, you can study that with dynamics, and there's a force and you can work out its motion. And that's because you've just got one of them. If you've got 2 or 3 cricket balls and they might bounce around a bit, you could also imagine studying that mathematically. But when you've got a whole gas in a container with 10 to the 23 or so molecules, that's much more difficult to study, as you can imagine. Working out where each individual molecule goes is just beyond complexity. So what you kind of do in StatMech is to say, I give up on working out the motion of each individual molecule, but I can work with averages and kind of variances for how spread out those averages might be, or how spread out the values might be from those averages. And there's a whole branch of physics which studies that. And despite the fact that you never know where any individual molecule is or how fast it's going at any given point in time, you can still make a lot of progress. And so it turns out with particle physics, you can think of it in terms of StatMech in a very useful way. And so in a way, my PhD was a bit in particle physics, but a bit more in statistical mechanics.
Okay. Yeah, that's a really good explanation. So where did you do your PhD?
I did it in a place a long way away called Australia, in Canberra. So I did my undergraduate in the University of Queensland in Brisbane, and then I moved down to Canberra to do my PhD in the Australian National University. So Canberra is the capital of Australia. So yeah.
And as I was doing a little bit of research on your background, I've noticed that you've traveled around a lot.
Yeah.
Do you want to kind of explain what led to those decisions of going from, Australia, and then I saw also Italy on there? And
yeah, so even in my PhD, the last year I moved to Sydney. My supervisor got a job in the University of New South Wales, New South Wales, not Old South Wales. And so I moved the last year there, which is great to have a year working and living in Sydney. And then I was very lucky to get a job in the University of Edinburgh as my first kind of paid academic post as a research fellow. And when I say I'm very lucky, I literally mean that. So long story, but bumped into someone having applied for but not been successful getting any research posts after my PhD. So I was working in a kind of government research lab in an okay job, but not really what I wanted to do. I bumped into a guy I'd met earlier from the University of Edinburgh, and I said, should I apply the next annual round of these applications for doing these research fellowships? Thinking he'd say, no, don't bother because you're not up to it. But then he said, oh, great, when can you start? So I had someone leave early, and so I was right place, right time. So yeah, I was very lucky. So luck can play a big role in your career. Okay, so unless you're Albert Einstein, then you kind of need a bit of luck, I would say. So I was in Edinburgh for that period of time at the end of that guy's contract when they left early.
Sure.
And then Southampton for 3 years. And then there was a research collaboration between the people in Southampton and Rome. So I lived in Rome for 3 years. which was an experience. Very positive, but also had some stress levels which were very high as well. But worked with some fantastic people. I mean, people who one became a Nobel laureate, one should have been, at least one should have been. So yeah, amazing, fantastic experience in terms of the physics there. And then I got a job in Swansea University, so I've been here ever since.
So I guess that's kind of the main questions that we try to ask everybody to get a background on, who they are.
Quickly ask, so when you came out of university, a lot of people will tell you that networking is one of the most important things to kind of find somewhere to go. Would you say that you kind of thought about networking as like, this is something I've got to do, or is it just a case of like, talk to as many people as you can?
I'd say to be the second. I don't think, especially when I was younger, I don't think I was a natural networker.
Yeah.
But my career path showed how important networking is. So the guy I met in Canberra, he was giving a keynote lecture in an international conference there. I had met him, as it were, I've networked with him in a sense, I guess, when I went to a summer school in Edinburgh, or in St Andrews in Scotland anyway, run by the people in Edinburgh. So during my PhD, I'd met him and kind of, got to know him. You might say networked, but was just interested in getting to know him. And so that was key. So without that, for instance, had I not gone to that summer school, I wouldn't have an academic job.
Yeah.
Had I not kind of made the point of talking with him a bit, I guess, then he wouldn't know who I was, and also I wouldn't have got a job. So, there's expressions, not what you know, it's who you know. I think that's a bit overstated in academia, but it still is important to put yourself about a bit, for sure. Yeah. Less important, I think, than in other roles, but it shouldn't be understated.
Yeah.
I actually did have a question about what it's like being a scientist in different countries, right? Because I bet it is quite different, but only in some aspects.
Yeah. Actually, it's not. It's very, very similar. So one of the great and most fulfilling and attractive things about working at academia is the people you mix with. And so when I was living in Australia, you would meet some people from other places, but not that many. And when you did, it was somewhat of a novelty-ish, I guess.
Sure.
But working in academia and research, then you're always rubbing shoulders with people from all sorts of interesting places. And so the reason that I really, really enjoy that is that, it's a bit of a cliche, but it's a statement of fact that everyone's basically the same. Okay, there's good and bad in everyone, and et cetera, et cetera, et cetera. But you don't see the artificial divisions created by lines on a map in politics. That just is irrelevant. And going to CERN, for instance, that is a huge microcosm. It's like mini United Nations. So you hear all sorts of different languages, different accents, et cetera, et cetera, et cetera, but everyone's working together for the common good. So I really, really enjoy that part of it.
Yeah, that is pretty cool, actually. I never thought about it as more of like a, different people from all around the world coming together for a common goal. I mean, that's pretty obvious, but I feel like
yeah.
And
CERN is a case in point because it was really set up deliberately with that in mind not long after the end of the Second World War. So there was really an deliberate idea to bring scientists together for the common good. So it would be bringing different people who'd fought on opposite sides in the war, for the common good. Initially, I guess, of Europe, but very much is absolutely international now.
Yeah, I think they did something similar with the ISS. I think that's why it's mainly cosmonauts and astronauts up there, or at least originally.
Absolutely. So I can tell you a bit about the backstory of the ISS, because it was pushed very hard, and the driving force behind it was a guy called George Abbey. He was the director of NASA's Johnson Space Center, and he has a link with Swansea. So he came and visited Swansea 10 years ago this year and gave a talk in the British Science Association's annual science festival. And he has a Welsh connection through his, I think, grandmother or mother or something, and has loves the poetry of Dylan Thomas, and that's how he kind of was involved with coming to Swansea. And we got him to open Oriel Science, which is something I can talk about later on. So our very first Oriel Science place was opened by this guy, George Abbey. So he saw the future as being very international, and he got NASA to work together with the Soviet Space Agency and kickstarted discussions to make the International Space Station. So his photograph is orbiting above our head because he's held in such high esteem that his photograph is on the International Space Station.
That's pretty cool.
So yeah.
I didn't know that. That's really interesting, actually. So kind of moving the conversation towards at least what I assume is your current research, what I've seen is about chromodynamics and lattice field theory. And that is just like so far. I tried to read about some of it. Please correct me if I'm wrong. I'm pretty sure chromodynamics is about the strong interaction, and how lattice field theory comes into that is, now this is where I'm stretching. I'm not sure if I'm right about this. Lattice field theory is about kind of similar to like defining a space-time metric, where the lattice field is kind of the space-time that you're putting it in. Is that right to a certain extent?
Yep, that's very much heading absolutely in the right direction. So the way you might explain it is that, again, going back to the cricket ball, they play cricket in Australia. Do they play cricket much here? Maybe. Do they? Okay. So throwing a cricket ball through the air, you can work out its trajectory. And there's, Newton's laws of equation. Newton, a very famous British English physicist, to give credit where credit's due. So you can work out the equations and you can work out where the cricket ball moves. There's a force, and there's the effect of the force on the particles. But those equations are fairly easy to solve. You can solve with pen and paper. So that's gravity. But with the strong interaction, so quantum chromodynamics is the theory of the strong interaction. That's the force that doesn't bind sort of planets and cricket balls together. It's a force that binds quarks together. And there's 3 quarks in a proton. So it literally is a thing that holds protons and neutrons and other particles like that together. So unlike gravity, though, it is an incredibly complicated, in some sense, set of equations. So you can't just solve them with pen and paper. So also the quantum mechanical. So in quantum mechanics, it's not like the motion of a cricket ball, which follows one unique trajectory. A quantum mechanical cricket ball would kind of go in a nice arc. It would also go around in circles in a spiral, around back behind your head, around the moon and back again. The quantum mechanical particle can take all possible paths.
Sure. Just
some are much, much, much more likely than other ones, but in some sense, it should include them all. And so you've got this strong interaction where the mathematics is very difficult, and you've got to sum up over all possible paths. And so what do you do? Well, the way you make progress is you use a computer. So you discretize space and time. And so you can say that the quark can sit here or at the next site in lattice site or the next site or so on, and it can't sort of sit in between. And that's just like engineers, that's the approach engineers use when they design skyscrapers or buildings. They break up their bridge into, boxes of the size of a cubic meter or something like that. Okay. So it's the same kind of way of going from a continuous theory and a continuous differential equations into like a finite difference. So, so you've got these quarks which can sit on these different sites, and then you have this equation which now has finite differences. So instead of like a continuous derivative, it's just change in y divided by change in x, where the change in x is a finite step. But all your continuous derivatives can be rewritten in terms of those finite differences, and then you can press play on your computer, and then it does everything for you. And the quantum mechanics comes in because all these different positions or trajectories or fields that the quarks can sit in, they have to sum over all possible different fields. So not just the cricket ball going in a parabola, but the cricket ball going behind your head in a spiral or something. So all those have to be summed over. And so then you've got the picture in your mind of this sort of box, which is a lattice, discretized, but it's kind of many copies of that because each copy is a different kind of trajectory, which is a quantum mechanical representation. And the true answer is when you sum them all up. And that's a lot like the molecules of gas in a box. because that's how statistical mechanics works. You've got particles whizzing around in that way, or another way, and so on. You don't actually know which one it is at any given point in time because you've got to sum up over all of them because you never know the motion of any one particular gas molecule.
Sure.
So you've got to shut your eyes and say it can be anything possible given some overall parameters. And so that way there's a very good analogy, very close analogy between statistical mechanics, studying lots of molecules whose details you don't really know in detail in a box, and the motion of quarks through the quantum mechanical sum over all the different trajectories. So, but big picture wise, it's like solving motions of things, but unlike gravity, which is a simple piece of mathematics, because it's very complicated, you've got to chuck it on a computer and then let the computer do that calculation for you.
Sure. And how long does it, so you can, that's like a simulation then?
Yeah, absolutely.
So how long does it take to run a simulation like that?
So some can take months for sure. Yeah. And so the numbers kind of, as it were, exponentiate. So they get very, very large very, very quickly. So, if you want to study 3 quarks inside a proton, well, for a start, you've got to make sure that your box that you're putting these 3 quarks in has to be bigger than the actual size of the proton. Because if it's not, then you're trying to squeeze your quarks into a small volume, and you're not representing a proton, you're representing a proton that's being squeezed. So that's not going to give you the right result.
Yeah.
So for a start, you're going to make your box much bigger than, or significantly bigger than a proton. And that's on one scale. The other scale is the question, how fine a lattice do you need to make it? So the proton's only got sort of 3 or 4 sites across it that the quark can sit, and that's not very good. It's like an engineer building a bridge across the Severn crossing, approximating it by sort of 3 horizontal beams. You wouldn't want to drive over that. So you'd want to make the lattice spacing quite small so that all your finite difference approximations are pretty close to a good approximation of your continuous derivative. And so that is another kind of limit. And that means you've got to have as many points as you can, which are small enough over a volume. So you're easily getting sort of 20 or 30 lattice sites across, which doesn't sound that many. But 30 lattice points across is pretty much okay. But it's 30 in space, the 3 spatial dimensions, and you also discretize time. And so, 10, 20, 30 to the power 4 is a very large number. And then you've got to simulate all possible combinations of the field.
Oh, I see.
So then that's another level of complexity. But fortunately, like the quantum mechanical cricket ball, some trajectories are much, much more likely than other ones. So the example of the ball going around the moon and coming back again, in theory it can happen. In practice, snowballs chance and hell. So of those zillions of different configurations, you home in on the ones which have got the highest probability. So it's a bit easier than you might think. But very quickly adds up to 10 to the 18, 10 to the 20 calculations. Wow. So more than there are seconds in the universe since the Big Bang. Okay, so it's off scale. Yeah.
The limiting factor of the simulations is the computational power.
Yes, but fortunately, if you look back in the last sort of 30 years or so, that these calculations, these lattice simulations of the strong interaction have been going, 2 things have helped make progress. Definitely computing power, which has increased orders and orders of magnitude, but also people have got clever with writing better algorithms. Okay. So to write a method that gets to your answer quicker, without making it any less accurate, there's been huge progress in that as well. It, in some vague sense, it often is involving kind of finding the inverse of a large matrix, in a sense. And there are clever ways of doing that, which can get to a good approximation of the inverse of a large matrix a lot faster in a much fewer number of steps. And so, as those algorithms have been implemented, you get progress much faster. Okay. So both computing power increasing and people being smarter with algorithms, both have maybe roughly produced an equal amount of speed up.
And does it get to a stage where you make the step a certain like you take it small, and then if you go smaller, it doesn't really make a difference. Like it's sort of like taking a limit, I guess, as you go towards zero. It's like,
Yep.
okay, now you can kind of see what it's going to do, and you can estimate to a good approximation that's what the behavior is going to be. Is that sort of the case?
It's exactly that. So
Okay.
I can show you plots where we've done exactly that. So
Yeah.
on the horizontal axis, we've got the lattice spacing, and so we get a result with a kind of quite a coarse lattice spacing, and then we run it again with a finer lattice spacing, which means it's much longer to do because we want the same extent, the same overall size to fit the proton in, and we have, say, twice as many lattice points. So that's that's 2 to the power 4 times more lattice sites because it's 4 dimensions. So much more time consuming. But yeah, there'll be another point, and then another point, and we kind of see the trend as that lattice spacing gets sent to 0, and that's how we would do an extrapolation. Yeah, absolutely. Yeah.
Is it worth, because obviously this is sort of like, it's not physics really, like you're doing the physics in terms of maths, and then you're sort of you're trying to describe it in words. Is it worth thinking about like how this affects our understanding of reality, or is it just worth thinking about? I'm sort of thinking about like, does the universe actually behave in this way, where it's like quantized distances in the universe, or is it just useful for simulations, but it's not really worth thinking about whether that's actually how it works in reality?
No, yeah, obviously these are very deep questions, and I think even Feynman was thinking about whether or not the universe was fundamentally discrete at its finest
sort of
length
like,
scale.
It comes into like, do we live in a simulation? Kind of thing.
Yeah.
But is it worth thinking about these things, or is it?
Definitely, yeah. So you never would know where that's going, where those thoughts are going. We work on the assumption that space and time are continuous. So even though we are discretizing space and time, we're just doing that as a kind of computational trick for us to get an answer. So we are taking the limit, as you said, as the lattice spacing going to 0. But a deeper question is the really, really fine scale. So even though the length scales I'm talking about are much smaller than a proton, so protons like a femtometer across, a 10 to the minus 15 meters across, and we're looking at things which are a lattice spacing which is sort of an order of magnitude smaller than that. That seems incredibly small, but in some sense, in the theory of particle physics and the standard model, there might be a kind of limiting length scale which is much, much, much smaller than that again. Is it where gravity and these other interactions, these other particle physics forces become of the same magnitude, because gravity is quite weak normally. And that kind of defines the length scale, which is quite interesting, where gravity is as strong as everything else, and so that might be a fundamental length scale where something new happens. And who knows what that new thing is? Maybe that's the actual size of this discrete universe which we might live in. But this is way, way, way smaller than this 10 to the minus 15 meters.
I've heard there's a thing called a Planck length. I've heard. Is it to do with that?
It is exactly that. So I mean, you've got big G from Newton's laws of gravity, and that's got some dimensions in it, and you've got other physical quantities also with dimensions in it. And when you try and make something which is sort of dimensionless by combining all those things, that's a kind of a way of defining some kind of length scale. And or at least you can combine those constants together to get a length scale, I guess I should say. And that turns out to be incredibly small. And I'm being recorded now, so I'm a physics professor. I'm going to get it wrong, but 10 to the minus 30-ish meters or something of that order. Okay, with a very large error bar. Google it. And so incredibly much smaller.
So we've been talking a lot about lattice field theory and how you kind of set up your simulations and stuff like that. But I saw specifically that you were going over QCM, something like that, quantum chromodynamics.
Yeah, QCD,
Yeah, and about that specifically at high temperatures. So what makes that different from, because the particles are going to be moving around faster? Is that something to do with it, or
effectively?
Because I feel like it's on too small of a scale if you're looking at quarks and not like. Do you know what I mean?
Yeah, sure. So so definitely my research and others in our collaboration, people working here in Swansea University, definitely looking at QCD. So QCD is quantum chromodynamics, so the strong interaction force we're talking about.
Mm-hmm.
And we're definitely looking at that at very large temperatures. So why do we do that? Well, because physicists want to try and understand nature. And at the earliest points in the universe, just after the Big Bang, as far as you know anything, it was very, very hot. So assuming that the strong interaction was really a force that happened in the early part of the universe, we need to understand if the nature of the force of the strong interaction, or QCD, changes at those high temperatures.
Mm-hmm.
So, and it turns out it does. So, and again, it comes back to statistical mechanics, which I guess you learn mostly in your second year onwards. So, and it's like kind of like a phase transition. So, think about molecules of gas in a box. That would be kind of a high temperature. So if we've got, say, steam in a box, that's water. But if it's high enough temperature and maybe high enough pressure, then the water molecules form a gas, steam. Okay. As you cool it down, they will condense, form droplets of water. If you cool it down again, it forms ice. So those are two phase transitions: gas to liquid, liquid to solid. And it's not that the water molecules are changing. They're not kind of changing their clothes and becoming another sort of molecule or whatever, changing it, putting it on an overcoat. They're the same water molecules. So all that's happening is that the temperature is changing. So there's something funny going on about how the interactions work, that they kind of change phase.
Mm-hmm.
And that analogy applies also with a strong interaction with QCD. And it turns out, we believe that at very, very high temperatures, the strong interaction is no longer as strong as we know and love it at ordinary temperatures. So to put some vague numbers on it, the force between quarks in a proton is equal to the weight of 15 tons. So 3 elephants, okay? The weight of 3 elephants on the Earth, 15 tons, okay? So, and these things are incredibly small, right? Much smaller than 10 to the minus 15. So how can something so small have such a strong force? And yet it does, okay? Mm-hmm. It does what it says in the tin. It is the strong force, okay? But as you increase the temperature, that force seems to stay constant for a while, and then it gets a lot weaker. And what will eventually happen is you go to high enough temperature is that the force between them is much weaker, and the quarks can move apart, and they're no longer bound together into protons.
Interesting.
So the protons melt. So thinking in terms of nature, that means just after the Big Bang, there weren't protons and neutrons. It was just too hot. So presumably there was quarks at some point, and they were moving around. It was really, really hot. And there's a temperature, as the universe expanded, naturally it got cooler because the same energy was distributed over a larger space volume, so it's got to get cooler. And at a certain temperature, the nature of the QCD interaction changed, and the quarks bound together into protons and neutrons. And so in effect, they've been bound together in the same protons and neutrons kind of thing since then. Mm-hmm. So how hot is that temperature? Well, we normally work in weird units in particle physics, but if you wanted to work in Celsius, it's billions of Celsius, okay, which is hot even for an Australian. So I've said that about 100 times. Anyway, so so it's incredibly hot. So and the really interesting thing is that in collaboration with lots of people, we've been studying this interaction and that sort of kind of transition. You might want to call it a phase transition almost. And it seems that it doesn't occur at one point; it occurs over a region. Mm-hmm. So there's a lower temperature where things start becoming a bit weaker. Then there's an upper temperature where it's got so weak that it's basically effectively free. So,
sure.
The idea that QCD had this one phase transition was the conventional understanding, but we are uncovering evidence that there's really these two upper and lower temperatures where over which this transition of quarks becoming free happens.
Mm-hmm. So it's not like it gets to this phase transition, then it continuously gets more. Like it continuously gets weaker. It's like two defined temperatures.
Yeah, it's a start and end point where at the start point, if you would study it kind of thing, you would see, that something's happening. Mm-hmm. For all the temperatures below that, it was 15 tons. And then at this magic temperature, it started to get lower than 15 tons,
Sure.
and it got lower and lower, less and less strong. And then at this upper temperature, it's now effectively zero.
Sure.
So it seems like a transition like that. Whereas most phase transitions happen at a temperature. So ice melting happens at normal temperature and pressure, happens at 0 Celsius, full stop. It doesn't slowly happen.
Yeah.
Okay?
Yeah.
It's well-defined single temperature.
Since gluons are the like force carrier for the strong force, at the beginning of the universe when it's really hot and quarks are kind of just moving around freely, I just want to, for my own sake, want to confirm, I don't know, is that quark gluon plasma then? Is that
Yeah.
like that new state of, not
Yes.
new, but like is that a different state of matter then?
Yep.
Okay.
So at the very high temperature, so above this upper temperature, the quarks are free, and so it's like a plasma. So it's, yeah, that is the quark gluon plasma phase.
Okay.
And why is it called plasma? Well, when we normally use the word plasma, we talk about an electric kind of plasma where the electrons in a neutral atom get ionized, leaving the remaining part positively charged and electrons negatively charged. And so they're electrically charged entities which move around, kind of like a gas, but it's different to a gas because all the kind of particles which make it up are not neutral; they're electrically charged. And so that's the electromagnetic charge is being broken apart, and each of the constituents, all the constituents, carry that charge. So it's exactly the same with QCD. So at low temperatures, the proton is bound together, and the equivalent of the electric charge of an atom, of a neutral atom, would be zero. The equivalent of the color charge of the proton is also zero. It's neutral. But if you were to start pulling the quarks out, it's like pulling an electron away from a neutral atom. Then you expose the fact that each of the constituents have got this charge, in this case a color charge. And so there's a plasma of now color charge.
I see.
Rather than electric charge and normal plasma.
Does that, like, knowing that the strong force changes at really, really high temperatures, does that get us any closer to an idea of a unification of the forces at the beginning of the universe? Knowing it can change?
Yeah, it would be a kind of a small step in that direction, not an insignificant step, but not a giant leap in that direction. But it kind of is linked to the unification of the forces in the sense that what happens is that the strength of the force depends upon how you measure it. So if you were to kind of have a proton, you fire another kind of proton or something else towards it. If you do it quite softly, then it interacts in a certain way. But if you do it with much more energy, then the strength of the force is not the same as it was when you did it softly.
Sure.
So the strength of the force depends upon with how much sort of momentum you are probing the force. So in that sense, you think about the strength of the force changes with the momentum involved. And momentum or energy or temperature, they're all, opposite sides of the same coin.
Yeah.
And so as you change the temperature, definitely the strength changes, analogous to kind of probing with different momenta. And so then you have the idea that the strength of the force changes depending upon your energy scale. And you can calculate that variation with energy, and you can do it for electromagnetism, for QED, so quantum electrodynamics, QED. So the photons force change in a certain way, and the gluons force for QCD change in a certain way. Gluons, it's 15 tons we're talking about in strong interaction. The electromagnetic is much, much weaker, but they run in different ways. And it seems that when you run it to incredibly high temperatures, they merge and they become the same strength at an incredibly high energy, about the Planck energy.
Okay.
And that gives a strong hint that that's a special point where things which were different at lower scales become the same at that magic scale.
Interesting.
They become the same, they're kind of unified.
Okay.
And so, yes, the things varying with temperature and things varying with energy leads to that unification picture.
So you said with the electromagnetic force, right?
Yep.
Is there any way to test that with, like, because I was reading a book last year talking about how the weak force and the electromagnetic force were theorized to, be the electro weak force. Is there any way to test that the electro weak force is, because like having that extra variable in there might change it?
Yeah. So no. So yeah,
that makes sense.
we talked about the electro. So QED. So the E is quantum electrodynamics, electric force. QCD, chromo force. So the strong force, the gluon force of quarks. We haven't talked about the weak force. So in particle physics, we kind of just accept that when we talk about electromagnetic, it's intimately unified with the weak force anyway. And so we kind of sweep them all together in a kind of a sense. And so everything I said before applies also to the weak force.
Sure. Okay.
So in a sense, we've kind of ticked that box. We already know that the electromagnetic force and the weak force are flip sides of the same coin. So that unification has already happened. So the next unification logically is to combine the electro-weak force with the strong force.
Yeah. Okay.
And then if that can be done, logically you think the next most difficult thing again to solve would be to combine that with gravity, which is all bets are off. Who knows? Yeah.
And I know Ben probably has a couple of questions, but I do have one itching question that I wrote down before I got here that I wanted to ask, which is on the topic of gravity. Now, this probably isn't in your expertise, but I just wanted to ask it anyways because you definitely know more than me about physics, hopefully. If lattice field theory, like, now I could be lost in translation here trying to read it on different sites and this and that, so my idea of a lattice field could just be wrong. But if lattice field theory is kind of like defining a metric that these different things live in, and if Albert Einstein's general relativity isn't just really, really close to being right, but it is like a really close approximation, kind of in the sense that Newton had really close approximations, but they're not correct, if that makes sense. But if gravity is actually just a result of space-time bending and it isn't a force, so that means that we would look into, for a quantum theory of gravity, if that exists, an understanding of quantum space-time and not quantum gravity, because that means it would be pretty much the same thing if my idea is getting across to you. So if a lattice field is kind of like explaining a space-time that it lives in, does that get us any closer to understanding if there is like a quantum theory of gravity, or if there is, like, if it's applicable at all in lattice field theory or anything like that?
No. Unfortunately not. So, but it might in some philosophical kind of way, but the lattice approach really is just a tool to solve some complicated mathematics.
Sure. Okay.
So picture it in that way. It's sort of level 1 sophistication. Okay, but looking at curved space-time and kind of Einstein's theory of gravity is like level 2, level 3 level of sophistication.
Sure.
So, and that's we in lattice field theory we don't go into those depths.
Yeah.
So think of lattice field theory as purely a computational trick to make progress.
Okay.
You certainly can have a lattice version of gravity, so you can have a discretized space and time, which does kind of follow the rules of Einstein's theory of gravity. And so, you can have curvature in there and things like that. But that's not what we do. We're much less sophisticated than that. So if you like, all we are ever trying to do is just to solve QCD full stop.
Yeah.
So we never have gravity in there at all.
Yeah, I kind of thought that would be the answer to it, but I just wanted to ask because I needed to have peace of mind walking out of here about that.
Yeah. So, it may be that someone much smarter than me comes up with an idea to do something along the lines of gravity and discretize it in a way, and magic happens, and they can show that they can get a quantum version of gravity. But that's above my pay grade.
Sure.
No, this is purely just a thought that I just had now, but is there a chance that gravity could not be fundamental and it arises from these other forces as just like a byproduct? Yeah, so that there's always that. So no one knows. It's like asking, is the electron fundamental? Is the quark fundamental? So going back in time, people thought the proton and the neutron were fundamental. And going back before then, the time of say Rutherford, people thought that the nucleus was fundamental.
And then going back earlier in time, people thought that, earth, fire, water, and air were fundamental. Not that past performance is any guarantee of future outcomes, but the progress in science really is about kind of understanding things at a smaller scale.
Yeah.
Number one. And number two, I would say unifying disparate things that at first sight seem totally unrelated, but in fact are caused by the same fundamental theories of interactions. And the beauty of that is that if you had to write down the equations to make a brand new universe, if the universe suddenly expired, you need to make a new one, how many equations would you need to write down? Well, a long time ago, there would have been lots of equations. But as time's gone on, because we've unified different interactions together, the number of equations you need to write down to rebuild a universe is smaller and smaller. And kind of the driving ambition of physics, of sort of theoretical physics, in a sense, theoretical particle physics, is to try and describe the entire universe with as few equations as possible. And you can also think about that in terms of the number of physical quantities, parameters, like Newton's constant of gravity, for instance, the electric charge, the mass of the electron, these things. As time's gone on, the number of those, what you call fundamental parameters of the universe, they've got smaller. So I'm not talking about the equations, I'm talking about the numerical values of things in the equations. A while ago, we would have had to write down the masses of protons, neutrons, pions, kaons, omega particles, all these things. Hundreds of particles, but now they all come from just 6 quarks. So in a sense, those hundreds of numbers of masses have now been distilled into just the masses of the 6 quarks, in a sense. And that's enough to derive all those. So, that's another way of characterizing the progress of physics in terms of the number of physical parameters you need.
I had a little bit more of a simple question that I know you would hopefully be able to answer is,
what's the meaning of life?
Yes, exactly. Why particle physics? Like, did you just kind of fall into that, or was that a decision, or?
Yeah, so that's kind of a deeply personal question, but in a nice way. I don't mind answering it. I've always wanted to do it. I remember when I was really, really young, 12 or something, my dad literally asked me what I wanted to do. And I said I wanted to do nuclear physics. I didn't know that there was. When I was 12, I wasn't sure that quarks existed. I don't, So, yeah, I just had this passion to look at the extremes. So, there's a bit of explorer mentality there. So, searching for things that no one knows the answers to. So that curiosity, I guess. So I was interested in astronomy as well. Many physicists, astronomy is the gateway drug into physics, and that certainly interested me. But the thing that floated my boat was the smallest things. So not really only, but from fairly early, I've always wanted to do it for those reasons.
Sure. Yeah. I remember we were talking with Sarah Roberts. That podcast just came out earlier this week. Well, I guess not at the time of recording this, it came out earlier this week. And she was talking about how she was talking to a student that really liked astronomy, and the student was like, "Oh, I really wish I liked science and this and that," and she's like, No. You realize astronomy is science, right? And I think that's like calling it the gateway drug into science is actually a weirdly good explanation, because a lot of people will really enjoy it and not kind of realize that just as scientific as everything else.
People have a misapprehension about what science is.
Yeah.
It's not fully appreciated what it is.
Just one last question about you. You said that it was mainly curiosity. I mean, to make your answer a lot shorter, the reason why you went into particle physics was curiosity. Do you think that's quenched your curiosity, actually pursuing a degree and then a PhD and now a career in it, or has it just made you more curious?
To use the gateway drug analogy, it may be inappropriately, but no, I'm still hooked on it. So I still need my fix, as it were. The research that I've been doing feeds the addiction for curiosity even more. So it not being quenched in the least. No.
Okay.
No.
Well, I mean that's a good thing. That's a good thing, because it would be bad if you said, "Well, I completely regret
Yeah.
going."
It's like an explorer. The more into an unknown continent, say, you explore, the more there is to explore, the more
Yeah.
you realize you don't know. So another analogy is the more questions that you answer, you think, great, I've ticked that box off. Therefore, there are less questions which are unanswered. And that's a fallacy, obviously, because once you understand something, it leads to 10 new questions which you didn't know existed, which appear before you as unanswered questions.
Yeah, sure.
So it's never ending. Yeah.
Mm-hmm.
Yeah.
Yeah, it's like you just check one off of the infinitely long list.
Yeah, but you don't know it's infinitely long. You can't
Yeah.
see the extent of it.
Yeah, exactly.
And every time you answer one, it's like climbing a mountain as an explorer. You think you've got to the top of the mountain, the end of the cliff at the end of the continent where there's now sea. It's not sea. It's a whole new valley and more mountain ranges to explore, which you didn't know existed before. I could talk about Oriel Science for a little bit.
Yeah.
So we're coming up to our 10-year anniversary. So it was started as a university outreach project. And it really started when there was a movie called Angels and Demons being shown in the local cinemas in Swansea.
Mm-hmm.
And that was based on a book by Dan Brown, who wrote Da Vinci Code, a huge selling book, fictional book. But Angels and Demons, that book was based upon a nugget which was factually scientifically correct about antimatter research in CERN. And our colleagues in our department in physics in Swansea University work on that experiment. And so in a sense, Dan Brown took the nugget of truth of our colleagues' research and then made it into a movie starring Tom Hanks. And so I contacted our university's marketing department and said, guys, you know this is going on. There's a connection with our university, with research going on. It's a big, huge movie. Don't you think you should do a press release, get these guys, these colleagues in front of a microphone to talk? Had nothing, which to say disappointed me would be an understatement. So if you can't get someone else to do a good thing, you've got to do it yourself. And so that's why we're going to set up Oriel Science. So the idea is that if you describe to someone that, you know, people in physics in Swansea University make antimatter, they'll go, wow, young kids, people who know Star Trek or whatever, antimatter, all this sort of stuff. Is it real? Yes, it is real, and they make it. And so the reaction is, wow, that's amazing. So that's from antimatter research, but it happens to research in biology, putting cameras in the back of albatrosses and watching them fly over mountain ranges. Every single area of research, pretty much, when you describe it, the reaction is wow. And so we kind of bottle that reaction, that wow factor, that's so crucial, especially in young people's minds, as a way of encouraging them to go further in their education. We capture that up into exhibits, which are interactive, and we put them in places people go in our city centre venue, Oriel Science. And we have school groups come in, they do workshops based upon those exhibits, and you can see it in their eyes, they go, wow. And they speak to our staff, often the university students who have begun that journey and a little bit older than the young visitors. And that conversations they have leads them to realize, oh, what, I can do that too. You're a university student. I didn't think I could be a university student. Well, yes, of course you can. Well, how do I do that? Well, you do this, you do A-level, blah, blah, blah. And so that helps encourage them on their educational journey.
That's pretty cool.
So it's bottling up that wow factor that almost all university research inherently has, that people don't realize. Universities are sitting on a gold mine of tools which will encourage young people to go further in education. They just don't realize it. Mm-hmm. And so that's been our mission. And yeah, it's been 10 years in the making, and now we're an independent charity. So we've been cut free from Swansea University, so we can do things as we choose. And Sarah, you mentioned before, is a trustee, and I'm a trustee as well. There's 3 other trustees, and we employ staff, and we're getting grant income to do our work and through other charities and so on. And yeah, so it's going very well.
That's super cool. Yeah, that just clicked for me. Is that the building downtown Swansea? Okay. On
the corner, yep.
In the main
That's
intersection.
The one.
Yeah.
Just up from Castle Square, the bottom of the high street, between the train station and Castle Square.
Mm-hmm.
Yep.
All right. I don't know why that took me so long to realize that. Okay, so I do have actually one last question that I was thinking about, and it is a little bit of a deeper question. I don't know how scientific this question really is, but it's something that I've thought about, because you can really, like, when you're looking at the universe and you're asking these questions about, particle physics or entropy or whatever it is, it seems like you can pretty much keep on asking why. Right?
Yeah.
And I feel like that's not very satisfactory, because you can kind of just ask why to anything and it just goes on forever. So I thought, does it make any sense for the universe to have circular reasoning in some way?
Yeah.
At some point, like it kind of, however it came into being, and then it kind of self-sustained itself, like using circular reasoning.
Yeah, so that's also a very, very deep question. So I'm not sure I can answer that, but one way I have of, which I think is along similar lines, is that if you think about kind of logic and philosophy, something that I don't have a very good grasp of, but you kind of have to start with some, what you might call axioms, some statements that people think are kind of inherently true. They're just inarguable.
Sure.
And then you can build things logically on top of that. And logic is a pretty powerful thing that the ancient Greeks and probably others before them developed. And this day and age, often it's not included when people make arguments. Logic goes out the window, which is very frustrating. But so logical argument has to be based upon something. But if you think about it, when human beings are born, and they're not born with that sort of ground truth of things that are just definitely known. So you kind of have to assume those things. But in logic, if you make assumptions, that's not a very firm foundation. And so kind of, as it were, because we were born in some sense knowing nothing in a way, but we have to build up our logical arguments. Inherently, it's built on a foundation of sort of quicksand in a way. And so, therefore, a deep question to ask is there a way, is there any ground truth that is inherently true that you can build arguments on? Or is it because we're human beings and we all have a finite lifespan, we're born at a certain point in time, that all our arguments at some fundamental level are built on quicksand? So kind of circular-ish in a kind of a way.
Yeah, I see what you mean.
There's an inherent unknowability about the universe due to the fact that we're finite beings in a way.
Okay, well, that's actually a pretty good answer. Yeah, I think that's a good place to end it. Yeah, that was podcast number 3 or 5. It's going to be one of the odd numbers, I think. It's
very odd. Thanks.
I appreciate everybody for watching if you've made it this far. And that was podcast. Okay, yeah, we already went over that. All right.
Thanks, Jack. Thanks, Ben.
Yeah, I appreciate it. All right, thank you. Bye, everyone.